another measure that let us deal with classification problems. And this is ROC curve. By the way, when we are looking at two class or binary classification problem, our classifier has two modes of output. Number one, just the class name. Classifier will tell us that this particular example or test set example is going to be classified as class positive or negative. The second mode is that the classifier will tell us the probability of this example for being in class A is 0.7 and in class B 0.3. So we not only get the class label from classifier, but also get the probability. Let's say we can draw a few examples here that can help us clarify this point. So we have a class, a red circle, and we can have, let's say, 4 examples of red circle, and we have a blue rectangle that is here. Put it here. Let's draw it here. This is our classifier. Let's say we have this line. To the right of this line, can you see the image that I am trying to show you?
Yes, I can see it.
All right, this is my classifier, the black line. To the left of this classifier, I have blue class, and to the right of this, I have red class, class A and class B. So can you tell me how many mistakes this classifier is making? Let's create two mistakes. Exactly. So for red class, it is making 1 mistake, and for blue class, it is making 1 mistake. So in case of confusion matrix, can you help me for the filling up the confusion matrix? Red and blue are the predictions, and these are the true values. Blue. So how many red are correctly classified?
2 over 3.
We just count the numbers.
Okay.
And how many blues are correctly classified?
3.
3. And then how many blues are incorrectly classified?
1.
And how many reds are incorrectly classified as blue?
1.
This is our confusion matrix. Now let's look at this. This particular data point, now test data set, test data point comes here. And this is our test data point that is, and next one is here. In that case, the distance between these two data points, like both have same class, but they are at a different distance from the classifier, right? So for this particular point, the probability to be in red class is more than this particular point, right? Do you agree? So this is far right. This is very close to the boundary, class boundary. How about this point? If I draw a point here. So it is half this way, half that way, right? So what will be the class of this particular point?
I think we can't determine the class of that.
Well, that is one thing. And the other thing that we can do is that we can give, instead of red and blue, we can give our prediction in terms of probability. So we say we have 2 columns, one for red and one for blue. And when we predict a point, we say this point, for example, this point is very near the class boundary. So we can say that it is in the blue class 0.7%, 0.7 in the blue class, and 0.3 in the red class. How about that? So how we will decide the class of this point? Whichever probability is larger, we will say 0.7 is bigger than 0.3. So eventually the label of this class is blue. So we will say it belongs to blue class because the probability for blue class is more. So classifiers do the same thing. In addition to giving us the labels, the prediction that we put in the confusion matrix, they produce probabilities. For this particular point, the probability that this point is in red class is 0.3 and in blue class is 0.7. For this particular point, we will say it is half and half. It is 0.5 and 0.5. So we will just toss a coin and classify this particular data point into class red or blue. All the points will give us a probability, a degree of belonging to class 1 or 2, class red or blue, class positive or negative. Our classifiers give us the probabilities as well. And based on those probabilities, we decide which class to assign a point. So if we work on the probabilities, what's the benefit? Number one, the points that are closer to the class boundary, like this one, they will be having less probability for being in the class compared to the points that are farther from the class boundary. So they are for sure in red class. So they have different probabilities. These 2 points have different probability of being in red class. Benefit number one. Benefit number two is that we can use these probabilities to give more weight to our calculations where we are more sensitive about red class, let's say. We want to detect an activity is fraud or not. Then missing a fraud activity can cost the company millions of dollars. So false negative should be highly weighted. So we can use these probabilities to weight high to the false negative. How? Using this visualization, I will explain. Let's say we have 2 classes. Our classifier will be giving probabilities that we put on the x-axis. Probability for in positive class will be higher than 0.5. Negative class will be less than 0.5. And the examples that have, let's say, probability 0.25, there are about 40 examples. On the y-axis, we have number of examples. And the probability of being in positive class with the probability point, let's say here 0.65, there are about 120 examples. So for probability, let's say 0.3, here is 0.3. How many examples do we have in the negative class? So let's assume we have 0.3 probability for the test point being predicted in the negative class. So looking at this diagram, can you tell me how many points do we have at 0.3 probability for belonging to negative class? So for if they are 0.3, that means it is less than 0.5, so we will classify it as negative class. So for this position where my mouse is pointing right now, we have 0.3 probability. And how many examples do we have? We will look at here and go here around
150.
Around 150 examples, right? So every bar is giving us a number, corresponding number on the y-axis. And on x-axis, we have the probability for being in positive class. So instead of looking at only the labels, red and blue, we are looking at the probability right now. One step before labeling. So how shall we label? We can say that beyond 0.5, if the probability is more than 0.5, the class will be positive. And if the probability is less than 0.5, then class will be
Negative.
In that case, if we make 0.5 as our threshold, how many false positives shall we have?
Around 75.
The below 0.5, we see some blue bars, right? These blue bars are the test examples that are actually positive. But because of our threshold, 0.5 probability threshold, they will be classified as
False positive.
They will be classified as negative, right?
Okay.
They are actually positive, but they will be classified as negative.
Negative.
Why? Because our threshold is 0.5.
0.5.
So if I make my threshold 0.25, then we will detect all positive correctly. Positive classes, only this one will be an error, but beyond, if we say more than 0.25, probability means class is positive. Then we are good with positive examples. We are making almost zero mistake, but we are making many false negative mistakes, right? We are making this many. Beyond 25, we can correctly classify positives, all of them, but these red bars will also be classified as positive. So they will be false positives. So you can now appreciate the role of threshold. If I keep the threshold at 0.75, we are correctly classifying all the negatives. But at the same time, we are making mistakes for majority of positives. Majority of positives will be classified as negative if I make my threshold as 0.75. This is the key diagram when we evaluate a classifier, and all our future modules, when we evaluate a classifier, will depend on your understanding of this diagram. So if the threshold is 0.75, we are saying that more than 0.75 class.
Yes, so anything beyond 0.75 will be positive and less than that will be negative, right?
Great. So the key number here is not the false positive or false negative. The key number is the one that is producing those false positives and false negatives. When we look at the probabilities, we need to decide a threshold, and that threshold gave us numbers that we put in the confusion matrix. Earlier, we said that confusion matrix is the base that generates different other measures: recall, precision, type 1 error, type 2 error, F1 measure. Everything is coming from confusion matrix, right? And confusion matrix is coming from
The threshold.
the threshold. The threshold that tells us beyond this threshold, class A, below this threshold, class B. In that threshold, when we move that threshold, the numbers in confusion matrix change. When the numbers in confusion matrix change, the other numbers will change, right? So this threshold is the key idea. If we are more sensitive about positives, we will have a threshold around here, 0.3. We don't want to lose any positive. If we are more sensitive about negatives, we don't want to lose any negative, and we can sacrifice some false positives, then we can make our threshold higher. If the importance of negative and positive is same, then we will keep our threshold at
0.5.
0.5 in the middle. But depending on the problem that you're dealing with, you will change this threshold near beyond 0.5 or below 0.5. What is more important to your problem? False positive or false negative? Which one you are giving more weight? Depending on that, you will move the threshold. How do we find the threshold? It comes from your problem. Let's say we want to convict based on the evidence. We want to convict, let's say, $500 penalty based on the evidence. Machine will convict that this person has committed a crime. So pay $500. Maybe petty theft crime. Now in this problem, you misdetect a person as a thief and the person pays $500. Consider this scenario, keep it in mind. The next problem is that you will convict a person and the person will be executed for murder. Now, if you execute somebody or put somebody in jail for life and the person is misclassified, the classifier or the machine has made a mistake of putting an innocent in jail, which scenario is terrible?
The second one, right?
Second one. So you are more sensitive about false positives. You don't want to convict an innocent. So you will change your threshold so that nobody gets go to jail for life because of the threshold. So you will let many people who have committed crime, you will let them go so that you can save somebody from going to jail. So you will change the threshold. So threshold will go up. So you don't want to convict some innocent. But for the other case, if somebody pays $500 and misclassified, it's okay. $500 is too much, but it's not life, right? So you will have little less threshold there. So depending on your problem, depending on your business, your business will tell you what is more important, false positive or false negative. If you want to reduce false positives, you will have to pay with more false negatives. If you want to reduce false negatives, you will have to pay with more false positives, right? So that balance comes from your context. But the key number here is the threshold. That threshold 50-50 mean you are giving equal weight to false positive and false negative. If we move up, that means we are giving more weight to the positives. If we move it down, we are giving more weight to the negatives. And it is now become very important to visualize the impact of threshold on false negatives and false positives. Here we can see 0.75, we can calculate more than 75, we will have this many correct, and all others, the big number of positives will be misclassified. All right, 50-50, we can see or 0.25 we can see. But how about all other numbers in between? There should be a way that we can quickly look at all possible options. Do you want to learn about that way?
Yes.
All right. So based on this threshold, we get two numbers, true positives, false positives, right? When we change the threshold, all numbers in confusion matrix change and corresponding precision and recall will change. Do you agree?
Yes.
So if we put precision on x-axis and recall on y-axis, for every choice of threshold, there will be a point on that plane. And we draw a line connecting those points, we get a curve. You want to see that?
Yes.
So all these points are what? Coming from the threshold, classification threshold, the probability threshold. If the probability is 50-50, beyond 50% positives, below 50% negative. In that case, our false positives will be around this point on the x-axis and true positives around this point, right? So when we change that threshold to 0.4, then our false positive increase. False positive will be 50%. True positives will be around 92 or 3%, right? So the more false positive we accept, the higher true positive fraction goes. If we want to have higher true positive rate, we will need to accept very high false positive fraction in the confusion matrix. And connecting these points, we get a curve. This curve we refer to as
ROC?
ROC curve. And now let's say we have another model that classifies into positive and negative, but the performance is slightly different. Can you tell me the performance? Here, keep this figure in mind. Do you see any difference? One difference is here, right? One difference is here. So these are two classifiers, right? Do you see this difference? Right? Here. These are two classifiers, two different decision trees, or one is neural network, the other one is decision tree, let's say. For the same data set, they are giving different predictions. The other difference is here, right? Right? Now we want to compare, looking at these predictions. We have actual classes as positive and negative. They're according to their color. These are the colors represent the actual class. And depending on the threshold, we will decide whether the classifier give us a probability. We compare that with the threshold. If the threshold is 0.5 for both the classifiers, how many positives, how many negatives do we get? So it's very hard to find it from this plot, right? Because there is a range of thresholds. And for every threshold value, we get a corresponding true positive and false positive. So it's better to look at the ROC curve for those two models. Would you like to see that? So you know the need for ROC curve now. We are now plotting both the curves from model A and B on same plot. So the blue curve is for model B, red curve is for model A. How would you decide which model is better? So
Yes.
you will compute, you will say whichever curve is giving more area under the curve. So if we compute the area under the curve for red, the area is more than blue or less? Visually, more. The red curve is giving better performance than blue curve. So we will look at the area under the curve, or AUC, of the ROC curve of a classifier. And area under the curve for model A is 0.92. Total area is 1. And 0.92 is under red curve, 0.86 is under blue curve. So you will choose the one that is giving you more AUC. So this is the way we compare and evaluate two different or more than two different models.